So we start again, and now we're armed with a Gibbs free energy diagram that's reacting zinc solid to form the zinc 2 plus aqueous cation plus 2 electrons, and we have the copper 2 plus aqueous plus 2 electrons going to copper, pure copper that plates out on the surface. So we've investigated that copper 2 plus, taking in the 2 electrons. We have connected that beaker to the beaker containing zinc 2 plus. But now, when we look at the Gibbs free energy diagram, we notice that the reactants are zinc plus copper 2 plus. And that means that I'm adding these two half reactions together. That's zinc solid plus copper 2 plus aqueous. The 2 electrons cancel out, and the product is zinc 2 plus aqueous plus copper in the solid phase. That's the copper atom that arrived at the surface. But the zinc reaction meant that zinc in the solid electrode popped off into solution to form zinc 2 plus, while the 2 electrons moved out of that electrode. That means that the electrons are moving in this direction. So the tug of war then between the copper cation and the zinc cation is won by the copper cation, and therein lies the determination of the direction of electron flow. So just to remind ourselves, that means that the Gibbs free energy delta G is less than 0, which is a spontaneous reaction converting zinc metal and the copper cation to copper metal and the zinc cation. So we've now solved the problem, and in fact those electrons move from the zinc 2 plus solution to the copper 2 plus solution. So now we know which direction the electrons flow, but we have a problem because those electrons are flowing out of the zinc 2 plus cation solution into the copper 2 plus solution, because the copper 2 plus has the greater ability to draw electrons to it. But as soon as that happens, we're going to develop a negative charge inside that solution because we're drawing electrons into it. At the same time, we're creating a positive charge on the left-hand beaker. Well, as soon as that occurs, electrons are repelled by the negative charge, attracted by the positive charge, and what was a nice healthy flow of electrons immediately stops. So we have to find some way of balancing the charge between those two beakers. And therein lies the genius of the salt bridge. The salt bridge is a connection between those two beakers, and if we have a salt made of potassium cations and nitrate anions, that means that this negative charge is going to draw those potassium cations into solution, neutralizing that charge. At the same time, the nitrate negative ion is drawn in by the positive charge, so we have NO3 minus entering to make up for the extraction of electrons through the flow of electrons through the external circuit. And so that was the last piece. The salt bridge was so important to the operation of this electrochemical cell that it was one of the major breakthroughs that Michael Faraday brought to the subject. So let's summarize, because the naming of these components of an electrochemical cell becomes extremely important for understanding how that electrochemical cell actually operates. So in the right-hand beaker, we know that we have the copper 2 plus aqueous cation reacting with 2 electrons to form the copper solid. And therefore, we know that reduction is taking place within that beaker. At the same time, we know we have to be extracting electrons from the left-hand side. That is, we are oxidizing zinc metal, zinc solid, to produce the zinc 2 plus aqueous cation plus the 2 electrons. So we're stealing electrons from zinc to supply electrons to the copper 2 plus cation. And that means that we have oxidation going on in the left-hand beaker. We also know that because copper 2 plus won the tug-of-war, it's the winner of electrons. And we know because zinc metal had to donate those 2 electrons that it is the loser of 2 electrons. So in the naming of this system, we name the electrode that is attracting cations as the cathode, because the cations are being attracted to that electrode in order to react with the electrons. At the same time, we name the system on the left as the anode because it's anions that it attracts, and those are the nitrate anions that came in from our salt bridge. So we have electrons flowing through the external circuit. We have the balance of charge sustained by the salt bridge. And we also have a naming scheme here, and there's one mnemonic that makes it very easy to set this up. Note that everything is alphabetical: oxidation, reduction, loser, winner, anode, cathode. And that is how we assemble an electrochemical cell, which is called a voltaic cell, because it creates a voltage.